Welcome. The title of today's notes is Graphs of Sine and Cosine Functions. And this one is going to require a little effort to kind of develop all the way through. So be ready with the graphing calculator, and let's see if we can get all these characteristics taken care of and do a couple modeling problems. And there's some good stuff with this. So anyway, let's start it out right away then. This comes from the previous notes worksheet. Just sketch a graph of y equals sine of x. So everyone, if you would, let's go ahead and get that elongated coordinate plane, kind of like that, if you would. 4 tick marks to the right, 1, 2, 3, and 4. Remember, pi over 2, pi, 3 pi over 2, and 2 pi. And then going clockwise, or in this case into the negatives there. And then let's go up to 1 and down to -1, something like that. And should, at this point, theoretically be able to draw what y equals sine of x looks like. If you need a graphing calculator to do it, you're more than welcome to, or just kind of watch me. But if you remember, sine is the one that starts at the midline, so right in between the max and the min, in this case right at the origin, and goes up, comes down halfway, coming through, and then something like that. So that would be one iteration in the sinusoidal loop. Kind of like that, and then obviously again comes back down this way. Let's get this going here. Something like that as well. Okay, that looks great. So a couple things to just note on this, a couple characteristics obviously to take care of. I would love for you to pause the video, that would be the ideal, and come up with these 5. But if you want to wait it out for a sec, that's perfectly fine, and I'll go through the process. So let's start with part A, and part A says what is the period of y equals sine of x. I like going from the y-intercept, which happens to be 0. So in this case, how many units does it take for me to get back to this exact spot on the graph? No, this is going down, so no, and there it is right there. So how many units is it from 0 to, remember this tick mark here is 2 pi. And this should make pretty good sense. Think about the unit circle, of course. If I go once around the unit circle, that's 2 pi units. Again, that's what just makes it such an amazing visual tool for us. You can really see it. If I go once around the unit circle, starting anywhere, if I go 2 pi units around the unit circle, I'm in the exact same spot. And so it should have the exact same sine ratio. Beautiful. So the period of our basic sine function, everybody, is 2 pi. Midline, halfway in between the max and the min, so in between 1 and -1. Again, it's a horizontal line. It would be y equals 0, but if you just put 0 there, I can live with that. Amplitude, everybody. Amplitude from midline to the max looks to be exactly 1 unit. Now, these two are great. This, we haven't really talked about it. I mean, we've talked about it intuitively, but we've never explicitly referred to the domain and range. So remember the domain here, the numbers that I can put in place for the input, for the x's here. And if you remember correctly, I can take the sine of any number, any real number. As I go around my unit circle, think about it in those terms. I can go around an infinite number of units in either direction. And you can see it here, everyone, the horizontal part of the graph. This just goes dot, dot, dot to the right, dot, dot, dot to the left, and it's just one endless sinusoidal wave. So domain is all real numbers. But the sine ratios that occur from taking sine of any real number is not all reals. There are some limits here, as you can see. I can never have a sine ratio above 1, and I can never have a sine ratio below -1. So my sine ratios are always in between these two values right here. So the dependent variable, when talking about the sine ratio, has to be in between -1 and 1, inclusive. Okay, I hope that works just in terms of graphical analysis. That looks great to me. Let's go get number 2. All right, so cosine. Now that we have this idea down, I can knock through this one and then start to move forward from here. Develop what I would call the more comprehensive sinusoidal functions. So these are your most basic, just y equals sine of x and y equals cosine of x. So let's go ahead and graph it. You can certainly work ahead of me if you'd like, but essentially it's the same sinusoidal wave, except cosine starts at the top, Kind of comes down like this. And it's kind of a max to max situation. It did not draw that great, but take it for what it's worth there. And let's see, just make sure I have it all. Something like that would do. Okay, again, maybe you'll draw it a little better than I can up here. Same scenario, everybody. If you could take a moment and maybe pause the video and do A through E, that would be ideal. 3 characteristics, and then 2 things we've talked about with all functions, domain and range. Let's see if you can pull it off. Well, I'm sorry, period first. I almost went to domain. Period, again, I like going from the y-intercept here. How long does it take for me to get back to that exact spot? Here it is, from here to here, and that's from 0 to 2 pi on the horizontal axis there. So always think horizontally with that period. How many units horizontally until I get back to that same point on the graph? And this should come as no surprise, but the period of the cosine function is exactly 2 pi. Picture yourself on the unit circle. Picture any point on the unit circle. Go around once on the unit circle, which is 2 pi, and are you in the same spot, and will you have the same cosine ratio? Sure. Midline, everybody, should be y equals 0. Amplitude should be 1. Domain, of course, I can take the cosine value of any number in existence, no exceptions at all. Positive, negative, from negative infinity to positive infinity. But when I take the cosine of any number, my ratios can only be in between -1 and +1. And we've looked at why that is in right triangles, and we've looked at why that is in terms of an angle, and so forth. So the horizontal over the direct distance, the x over r, can never be above 1 or below -1. Okay, so that's pretty much putting some of those foundational pieces together. Now it's time to extend this out a little bit, because what I'd like to do is start modeling things that have different periods than 2 pi, different midlines, different amplitudes. We have to figure out how to pull that off. Okay, so the way it's going to work out is it's really all based on the 10 transformations from first semester. So I wrote those on your paper here and up on my board, but all of these actually go in line with these trig functions very nicely. So we shifted 4 directions, up, down, left, right. We did 2 types of reflections, y-axis and x-axis, and we did some stretches and compressions, both vertically and horizontally. So what we're going to do is grab the graphing calculator and let it help us out here. See if you remember some of these transformations from first semester, but after I label the transformation in this column right here, let's graph it and see which characteristic changes based on the placement of my values. So what we're going to do is go from a parent function to the transformation function. So here's what I'm looking for, everyone. Let's start it out with y equals sine of x, and then y equals 3 sine of x. So taking the function and multiplying it by 3, do you happen to remember which of the 10 transformations this would be? Well, if you remember correctly, actually, this one is what's called a vertical stretch. By the way, anytime you affect the function, it's vertical. Anytime you affect the input, it's horizontal. So in this case, I took sine of x, the whole function, and multiplied it by 3. It had to be a vertical transformation. Now watch what happens, everyone. Let's grab the calculator. You do it with me. I'm going to go back to my y equals and clear what I had in there. And I'm going to type in sine of x. And then in the next one, everyone, I'm going to type in 3 sine of x. And all I need you to determine is which characteristic changed, if any, if any. So let's graph that. And when I vertically stretch your basic sine function, it looks like the period is still the same. It looks like the midline is still the same, but I stretched upward and downward there, so the amplitude changes. And so now I have a direct way to affect the amplitude, as you see. The number out in front is going to affect the amplitude. Excellent. Okay, let's take a look at the next one here. Y equals cosine of x, and now y equals negative cosine of x. Which transformation is this, everybody? Well, it is the x-axis reflection. Now this is going to come up a little bit for us. So keep in mind this negative piece. I'm going to go ahead and pick up my calculator here. You're doing it with me or you're watching the screen. But basically I'm going to go ahead and type in cosine of x in the first one, and then just a negative cosine of x in the second one. Keep in mind this one. Is there a characteristic that changes? Let's figure that out first. So it's tough to make heads or tails of this, but here's the original cosine function on its primary rotation, starting at the max, ending at the max. In this case, though, when I flip it, it starts at the min. Keep that in mind, everybody, and ends at the min. So it flips over. Instead of going max to max, it goes min to min. By the way, did any characteristic change? No, absolutely not. So in this case, how about just a little dash right there? No characteristic change, but it did change cosine. Instead of starting at the top, it started at the bottom. Okay, let's do the next. Instead of sine of x, it's just a sine of x plus 2. This is the first one that I teach when doing transformations. Should be a vertical shift. Should be up, by the way. I'll put that in there. And let's go ahead and check it out. See which characteristic changes, if any. So I'm going to go on back, everyone. You're with me on it in some way, shape, or form. So I'm going to type in sine of x. And then I'm just going to be a little careful on this. I'm going to do sine of x. I have to close off that parenthesis. And then I'm going to add the 2. Hit graph. There's the first. There's the second, everyone. Everything's moved up 2. Period change? Nope. Amplitude change? Nope. Midline changed. It went from, let's look at it, here it is, went from y equals 0 to now right in the middle there, y equals 2. Amplitude is still 1, everybody. Still 1 unit from the midline up, but it's the midline that changed. Okay, so now you can see how to affect the midline. Put a number on the back, and it affects the midline. Put a factor out in front, it affects the amplitude. Beautiful. We're already developing some good stuff here. I'm on to my next screen, and let's see what we have. Well, this is a good one. This one happens to be changing the input. So this is a horizontal shift. And if you remember, minus moves it to the right. Keep this in mind. Horizontal shift to the right, excuse me. And let's see if any characteristic changes here. I'm going to go ahead and see this in action. So I'm going to get rid of that, get rid of that. Let's go cosine of x, and then cosine of x minus, and then pi divided by 2. Okay, so something like that right there. Let's take a look. Should every point, I believe, is going to move to the right pi over 2 units. And there it is. So let me track a couple points for you so you can see this point, everybody, moved right pi over 2. Let's see, this point moved right pi over 2. This point moved right pi over 2. Well, interesting. Did anything actually change? No, no characteristic changed, and we'll put that up momentarily. Here's what's really fascinating about this. Focus on that transformation, everybody. In fact, let me get rid of this one so we can see it. Look at the cosine of x minus pi over 2. And does that graph look familiar? Oh, it should. And if you think about it, cosine of x minus pi over 2 is the exact same thing as y equals sine of x. This is your basic sine function right here. And there's your connection between the two, basically. I told you they're interchangeable. One is essentially a horizontal shift of the other. So sine of x is really cosine of x minus pi over 2. And cosine of x is really sine of x plus pi over 2. So they're just shifts of one another. Okay, enough ramble in there. No, nothing changed, though. It did shift. So just keep that in mind, but not one of the 3 characteristics. There'll be a 4th characteristic coming up in just a little bit. Oh, let's see, cosine of 2x. It looks like an input change, everybody, so this is going to be horizontal. This one's always a little bit tough, but if you do remember correctly, this should be a horizontal compression from first semester, horizontal compression. So let's see what happens when I horizontally compress this graph, see if any characteristic changes. So let's clear that out. Looks like just cosine of x, cosine 2x. Graph, and first one, and now the second one, horizontally compressed, all those points coming inward. And what changes when I do that, of course? Well, it's not the midline, not the amplitude, it's the period. And now we found a way, everybody, to affect the period. Throwing a number in front of the x is going to affect the period one way or the other. And here's why, everyone, because this, instead of a 2, it looks like I've got 1/3. If you remember from first semester, everyone, this is what's called a horizontal stretch. So picture that, if you would, please. I'm going to go ahead and graph it. You can just watch up here. Let's clear these out. And I have sine of x, and then sine of 1/3 x. And it's not great to see, but you can kind of tell. It looks like I have a min here and a max here. But this is just horizontally stretched. Midline is still the same. Amplitude still the same. The only thing that is dramatically affected here is the period. And so now we've got our big 3 and where it goes in the sinusoidal function, actually the equation itself. And so it's time to put some of that together here. And so that's what I have on your sheet. Let's go get them. So let's start out with the easy piece. It says in the equation y equals a sine of x or a cosine of x, the absolute value of that number, because everyone, theoretically, I can throw a negative out in front here as well, and that does something to the graph. So this can be negative, but amplitude, it can only be positive. That's why I wrote it as the absolute value there. But essentially, numerically, this a value is going to give us the amplitude. Those two go hand in hand. The other thing we found is putting a number on the back. That's going to be what's called our d value, as you'll see. So d is going to represent the midline. So the factor out in front, everybody, in essence is your amplitude. The number on the back is basically your midline. And then let's see, I have on your paper here, remember the equation of the midline is just, it doesn't make too big of a difference here, but just remember it's a horizontal line, so that's all. Okay, now, here's the thing. Good news, bad news with this one. Good news is we know how to affect the period of the sinusoidal function. I just have to put a number in front of the input. So this will change the period of each of these from 2 pi to something else. The bad news is the period is not this number. So when I graph this, the period is not 2. The period is not 4. And the period is not 1/2. So we have to figure out a way to get the period using those values. So I'm going to graph these 3. You can kind of look up on yours as well. If you want to graph with me, great. If you just want to watch up here, let's figure it out together. But basically, I'm going to type in cosine of 2x and graph it. And I guess what would be the period for this particular function? So first and foremost, from the y-axis, we're at the max. How long does it take to get that to that exact same spot? It looks like right here, which is 2 tick marks on my horizontal axis. But remember, this is pi over 2, and this is pi. So from here to here, everybody, the period to me looks to be exactly pi units. Okay, so if the b value, that's what we're going to call this number, everybody. If the b value is 2, the period is pi. Now remember, the bigger the number, the more compressed it is. Oops. So let's see this, and now again it's more compressed. Now everybody, look at the period here. I'm just going from here to here. That's it. Just the first tick mark. And the first tick mark on that z trig window is pi divided by 2. So when the b value is 4, yikes, the period is pi over 2. Last one here, and let's see if you can figure out the pattern, everyone. Let's go get them. I've got 1/2 x. I hit graph. Ooh, tough to do from the y-intercepts here, by the way, because I can't see how long it takes to repeat. So the only spot I can see from repeating is from here all the way to here. So here from -2 pi all the way to positive 2 pi. That's how big this stretch was. And so from negative 2 pi to 2 pi, I'm getting a period of 4 pi as a result. Okay. Well, guys, let's see what it says on your paper and then see if we can come up with a conclusion. So in the equation, y equals sine of bx or cosine of bx, the b value changes the period. Absolutely, the b value changes the period. Use your results from the above equations to write a formula for the period in terms of the b value. So if b is 2, the period is pi. B is 4, period is pi over 2. And if the b is 1/2, the period is 2 pi. I will give you one hint. It uses the idea of the normal, how shall I say this? The basic period for the basic sine or cosine function is 2 pi. So you're going to see 2 pi pop up. Okay, here's how it works. I take 2 pi and I divide it by b. That's how it plays out, everybody. And you can see that here. 2 pi over 2. I'm going to just write this off to the side. 2 pi over 2. There's pi. 2 pi over 4. There's pi divided by 2. And then 2 pi divided by 1/2, well, remember, dividing by 1/2 is the same as multiplying by 2. And so 2 pi times 2 is 4 pi. So that's how we're going to get the period, everybody. If I give you a sinusoidal model, you can come up with the period based on this right here. That's the connection. Sometimes, though, a lot of problems that you're going to do for me, I'm going to give you the period. You're going to have to come up with the b value. And so the way this works mathematically, everybody, is the b value can come up, the period can come down, and the nice thing about this is, oops, that's weird. Let's pause this for a sec. Sorry about that. Must have hit something there. But the nice thing is, it's the same thing. So to get the b value, which you're going to be doing for me, it's also 2 pi over the period. So write all this down. We're going to put it in a variety of places and utilize it. Those are your big three. There's a fourth one coming up momentarily. Let's go get them. Okay, and it says, look at the function y equals sine of 2x minus pi. Factor the 2 out from the parentheses. The function then becomes, okay, and then as a result, what is the horizontal shift? So we're going to be a little careful with this. This is one, the way these are written, might throw you off just a touch. So pay close attention here if you would. So here's what I'm thinking. If I look at this piece right here, what I'm going to do very simply is factor out the 2 from each of these terms right here. So when I do that, I get a sine of 2, and then what would go here when I factor out a 2 from 2x? I hope everybody would be in agreement with me. It's just the input, the x value. Now, here's the minus. When I factor out a 2 from here, essentially what I need to make that pi is that has to be now pi divided by 2. So when I factor out a 2, essentially I'm dividing this by 2. And now this 2 comes out, and this is actually the same thing as this up here, just now in factored form with that 2. Now, everyone, think about first semester and using horizontal shifts. A shift occurs when I replace the input, which is x, with x plus or minus a number. Well, here, everybody, instead of the horizontal shift being pi, which some students would like to think, the horizontal shift is actually pi divided by 2. And that's the case right here. So here's where we're going to have to be just a touch careful, and you can really see where this horizontal shift comes in. Now, you don't have to do this every time. Basically, to get this number right here, you see it has the c value and the b value in place. It's really c over b. And so long story short here, in the equation, because you're going to see a b and a c inside the parentheses simultaneously, it's the c over b value. Please write that piece in here. Not just c, everybody. It's c over b that represents the horizontal shift. For trig functions, it's not always called the horizontal shift. It's called, most of the time, a phase shift. So write that in there for me. So you'll hear me put it together as the phase shift of the graph. So c over b, everyone. Okay, Well, 4 characteristics, everyone. Let's put them together and try a couple examples and just move forward from there. So in the equation, and guys, box those 2 up. Those are your beauties right there. Those are the ones you're going to be looking at quite a bit. 4 components to make a comprehensive sine or cosine function. A, B, C, and D. And now what we have potentially seen as each one of the characteristics is embedded into the model with A, B, C, and D. How they're embedded is exactly what we just investigated. Absolute value of A, everybody, is the amplitude. Midline, the equation is y equals d. Okay, just that d value, think midline. A value, really think amplitude. Period, what we found, everyone, is that the formula for the period is just 2 pi over b. And the phase shift, again, just be a little careful with this one, please. The phase shift is not just c, it is c over b. And if you have a question with my little factoring technique up here to see that piece, here it is. Here's c, here's b. That's how it works theoretically. So that's your phase shift. Those are your 4 characteristics, everyone. Amplitude, midline, period, phase shift. We're going to do an example with this to kind of back it up here, maybe look at a graph, and then do one using the graphing calculator. So, example 1. Find the amplitude, phase shift, midline, and period of the function. Now here, everybody, is where I would ask you to pause the video for about 2 or 3 minutes and come up with these 4 characteristics for each one. So amplitude, phase shift, midline, period. No particular order, makes no difference to me how you pull it off. But actually, I would encourage you to do both just while you're thinking about it. And then come on back in just a couple minutes and see how you did on 8. If you can go 8 for 8 on these, you know exactly what you're doing. It's all good stuff. All right, so please pause the video for a moment and then come on back and we'll see how you did. Okay, here we go. So amplitude, everybody, comes from the number out in front. A is 1/2, and the amplitude here is 1/2 as well. Now, a couple ways to kind of do the phase shift, everyone. I'm going to skip that for a moment, so hold on just a sec for that. In fact, I should have talked about that before, but I'll take care of it here. Midline, everybody, is just y equals -1. If you didn't put the y equals, don't worry about it. Period, everyone, is 2 pi over 4, which is pi divided by 2. There's your period right there. Okay, now the phase shift, everyone. And you don't have to write this on your paper, but basically the default for a phase shift is bx minus c. So in this particular case, in terms of the c and the b value, I would argue, and again, you don't have to write this if you don't want to, but I would argue theoretically, when you see a plus in there, it's really 4x minus -pi. So truly, it looks like the c value is -pi and the b value is 4. So you have a couple ways to kind of write this. I'll be fairly flexible with you on this piece, as we're not going to do a ton with it, but should be comfortable with the idea. That would be one way to write the phase shift. End of story. A negative phase shift looks great. What that really means, and you've seen this before when we've done transformations, theoretically, when you see a plus inside, if you remember correctly, it moves it to the left. And that's what a negative phase shift is telling you to do, is to go to the left. So I don't care how you write it. This, you don't have to write to the left. That tells it to me automatically. Or you could exclude the negative and just give me the direction on the back. You could say pi over 4 to the right or to the left. In this case, to the left. So either one right there would work. All right, let's see how you did on the other one. Amplitude, guys, is always positive. Remember, there can be a negative out in front. We'll definitely talk about that piece on the next notes worksheet. But amplitude is positive, so 3/2. Phase shift here, everybody. Again, this is bx minus c. So b is 2, c is just pi over 3. So this is a good one right here. I have pi over 3 divided by 2. And I'm going to have to sort of cross this stuff out and come back to it. But pi over 3 divided by 2, I like doing this. I don't know if I've shown you this trick before with a quick compound fraction like this. do what's called the outside or inside trick if you're not sure how to do pi over 3 divided by 2. So outside, pi times 1 is pi. Inside, 3 times 2 is 6. And that would be it right there. Essentially, that's your phase shift. Or again, if you want to emphasize, you could write pi over 6 to the right. Again, not necessary, to be honest, not necessary. A positive phase shift implicitly tells you you're moving to the right. Okay, now let's come back to the midline there. Midline is just y equals 2 from the back. And period, everybody. 2 pi over 2, pi units. And those are your 8. I'm hoping you went 8 for 8 for the most part there. If there are a couple things to clean up, so be it. But I hope that looks good to you. See what we've on the next piece. Oh, you know what? Let's skip drawing this out. I'm not going to make you do that a ton. But what I was hoping you would see here with your parent function and your comprehensive function, all of the characteristics. It's kind of tough to see with the phase shift, but you would see an amplitude change to 2, midline change to down at y equals -1, period would be pi, and you would see a phase shift going to the left pi over 2. Sometimes it's tough to see all of that. And again, the way I've designed this course, you're not going to be doing a lot of point plotting with this. I'll tell you what, why don't we just take a very quick peek here, see if we want to include anything there, and then just move forward. So 2 cosine 2x plus pi and then -1. So again, you can kind of see a couple things. Notice midline especially down at -1. Amplitude now is up at from here to +1, so that's 2 units. Period is pi from y-axis to here, so that's pi units. It's hard to kind of see the horizontal shift, but there is also a phase shift with all the other stuff of going left pi over 2, including the axis of symmetry right here. Again, I won't get into a whole lot of detail with that. I won't make you point plot and try to sketch some of these out by hand, so I guess that's good news. I'll tell you what, though, I'd rather focus our attention on the last one there. So a sinusoidal piece of data that we're going to take a look at. We're going to need our graphing calculator for this piece. So refocus if you can, and let's do the example 3 as a result. So NOAA provides the following table for the length of day in Boulder for 5 given dates. And so what we're going to do here is find a sinusoidal regression. Daylight hours will be our dependent variable. So here are the daylight hours, everybody. And the day of the year will be our independent variable. And what we're going to do is write a model for something of this variety right here. And if you think about the number of daylight hours over the course of the year, kind of fits the criteria for something that is sinusoidal in nature. Remember what we've seen so far, everybody. Sinusoidal models, first and foremost, are periodic, meaning the cycle repeats again and again and again. And certainly the number of daylight hours repeats again and again and again, year after year after year. So it's periodic. And it also has a max and a min. So a longest day and a shortest day, just like a sinusoidal model has a max and a min. So the nature of this data really fits nicely with the concept of a sinusoidal model, and we'll see how good that model is momentarily. All right, well, let's bring it up. So at this stage, you've done a variety of models with me and probably with previous teachers. So let's do a couple things first. If you have anything in the y equals, clear it out. I'm going to turn my stat plot on because I'm going to play around with this. So I'm just going to go right up there and hit enter and turn it on. And then let's go. And if you've seen me do this before, I've always talked about regressions as 3 steps. Enter the data, view the data, and then model the data. So what we're going to do is enter the data first. So everyone hit stat and then go into edit. If you have some stuff in here, please clear it out. The easiest way to do that is go up to L1, press clear, and then enter. And then go up to L2 and press clear and then enter if you need. So X is going to be our list 1. Y is going to be our list 2. X is the day of the year, of course, the independent variable. So that's what I have, 1, 91, etc., etc. here. Let's get those in quickly. You're probably a quicker typer than I am. But please do this with me. Don't just watch up here. I need you to be able to execute some of this as well. All right, now we have to be a little careful on the number of, well, the daylight hours, the dependent variable here. I don't want to type in 9.25 for 9 hours and 25 minutes. Remember, 25 minutes is 25/60ths of an hour. So there's a nice way to do this on the calculator, so why don't we just do this together? So it's 9 and then plus 25/60ths. So I'm going to do 25 divided by 60, kind of like that. So you can type that in just like that. Just be careful that you don't do 9.25. If you want to convert it beforehand or whatever, I don't care. But there we go. That's the number of daylight hours on January 1st. Now, everyone, let's go ahead and do the others. So 12 plus 39 divided by 60, and then 14. So July 1st looks great. Almost 15 hours of daylight there. And let's see, let's get these others. And last one for me. Okay, so we have our data in place. I hope you have yours. And mine's looking pretty good. So remember how we've kind of discussed this before? Enter. Now view it. Hit zoom at the top, everybody, and just hit number 9. And you can see, there we go, there's one iteration in what would be a sinusoidal loop. And so now what we're going to do is model that with the regression, everyone. So I'm going to hit Stat, move it over to Calc, and as a matter of fact, I'm actually going to go up because it happens to be the last down there. And there it is, everybody, sinusoidal regression. And so what we're going to do is ask the calculator to come up with one in just a moment, and we'll put that together. Now, I'm going to put this into the, I'm going to have it paste our regression into the calculator. Perhaps I've shown this to you before. If not, no worries. This is optional. I'm going to hit the vars button, move it over to the y. It is a function, and I'm going to put it into the y1. So basically, I'm just going to tell the calculator to paste whatever it comes up with into the y1. And I hit enter. Now notice, look at the A, B, C, and D. The only difference, everyone, is that they do a plus here. It really doesn't matter. Ours still works out the same. But basically now it'll just be plus the negative. Ours would be minus a positive, but it's the same. So everyone, let's come up with this. We could talk about amplitude and periods and midlines and all that good stuff. But let's go 3 decimal places on this. So please, for all these sinusoidal models, let's go 3 decimal places. And you can write what I'm writing here. I have it on my paper. So basically, I've got this as the amplitude. 2 pi over this would be the period. Phase shift there, because it's not a perfect sine function or cosine function, needs to be shifted. And here's the midline, everybody, kind of the average, so to speak, a little over 12 hours, as you see. And that looks great. There is our sinusoidal model to 3 decimal places. If I know the day of the year, then I should be able to come up with the number of daylight hours. And I should be able to reverse it too, which we'll definitely do over the course of this unit. I'm not going to do part B with you, but what I'd ask you to do is part B, is figure out which day of the year this is, plug it in for X. As long as you're in radian mode, you should be able to figure it out. I'm going to do just 1 or 2 other things. Again, I'm going to have to leave letter B blank, but I just want to show you just 1 or 2 other things. Think about the period for a second. I'm just curious myself, but let's see how close it came to what would be a reasonable period here. So take 2 pi, everybody. And remember, the period is 2 pi divided by b. So there's our b value. If I do 2 pi divided by that, now notice it's not perfect, but we certainly would assume that it would be around 365. And so that's pretty good in terms of a model, pretty close, all things considered. And I wonder if I changed if I used different decimal up there, if it would change it, but probably not too much. And then I'm going to hit graph as well, and you can kind of see that the calculator is able to give me a nice sinusoidal regression on this. I would love for you to kind of predict the number of daylight hours for whatever day you're viewing this, and then check. It'd be great to just hop on dailycamera.com or something like that, or whatever the case may be, and I'll bet you it's really close to what's actually the number of daylight hours for this particular day. Okay, good. So please, you do need to be comfortable with the technology here. So if you're not, please ask. Don't just let it slide. You'll see it on your homework. You'll see it on the take-home quiz. You'll see it on the assessment and so forth. All right, a lot to go through in this particular lesson. I hope it made sense to you, and you're starting to see the characteristics embedded in our beautiful, comprehensive sinusoidal models. Thanks for listening, of course. I appreciate it. And obviously, I always state it, but I'll say it again. If you have any questions, don't hesitate to ask. That's what I'm here for.